Okay, so in this video we will talk about a simple generalization of the Deutsch problem called Deutsch Jozsa problem or the Deutsch Jozsa algorithm. Now, in the previous algorithm, the function was defined from a binary set 0, 1 to 0, 1. Now in this case, in the Deutsch Jozsa problem, the given function is from 0, 1 to the n to 0, 1. Okay? Alright, so now we assume that f is given as a black box, similarly as earlier, and we assume that f is either constant so assumption f is either constant, meaning that f of x is all same for all x in 0, 1 to the n. Okay? So we assume that f is either a constant function or a balanced function. In this case, balance means that f of x is 0 for exactly half of the inputs, and it's 1 for the other half. Okay, so it's half-half. For half of x, f of x is equal to 0, and for other half, f of x is equal to 1. Okay, it's not some other ratio. It's not like 1 to 3 ratio. It's exactly half-half. Okay, so that's our assumption. So for instance, if f was a function from 0, 1 to 0, 1 over 2 to 0, 1, then that means there are 4 cases, right? 0, 0, 0, 1, 1, 0, 1, 1. Function f is balanced if for exactly 2 inputs it maps to 0, and for the other 2 inputs it maps to 1. Okay, so it's exactly half-half. All right, now, and the problem is the same. Given f as a black box, the quantum version of f, of course, we're talking about uf, and we're going to define it in a moment. We want to know whether f is a constant function or a balanced function. Now, classically, using classical algorithms, the solution requires at least the classical solution requires how many queries? Well, it requires 2 to the n minus 1 plus 1 queries, right? In the worst case, so let's think about this function. In the worst case, what we could do is that we could evaluate f for all inputs, right? And there are 4 cases here, so it's 2 to the n divided by 2, that's 2 to the n minus 1. If it's all 0 up to this point, we need to evaluate 1 more, right, plus 1, to see whether the function is balanced or constant. If the next evaluation gives us 1, then we know for certain that the rest of the outputs will be 1 as well. So we know instantly that the function is balanced in this case. But if it's 0, then we know that the rest of them will be 0 as well. And in that case, we know that the function will be a constant function. So it requires exactly this many queries to determine whether f is a constant function or a balanced function. Okay, now surprisingly, using quantum computers, and using an appropriate quantum algorithm, it only requires one Curie. There's only one. With only one evaluation of f, I can know whether that given function is constant or balanced. So we have an exponential speedup, right? It requires exponentially many steps for the classical computer to determine whether a given function of this form is constant or balanced. Whereas in quantum computing, using quantum algorithm, it takes constant time, right? It's big O1. So let's see how to solve this problem. Now, f is given as a black box. Of course, we want the quantum version of f. So uf will denote the quantum version of the function f, and uf will be given as a black box. Okay, that means we can evaluate uf, but we cannot look inside and how it's defined inside actually. All right. So uf similarly will be given in the form of and the first register of uf will be an n-bit string, okay, an n-qubit register. And to separate this from a 1-qubit register, I'm going to use a boldface. In the lecture note, I use a boldface letter. So let me denote the boldface cat x, meaning that x is an n-qubit register. Okay, boldface x. Whereas the fancy x that I usually write, so let's assume that this x denotes a single qubit. Okay. Whereas this plainly written x on the right-hand side denotes an n-qubit register. All right. And then in the second input of uf, we have a 1-qubit register, y. Okay. And then this maps to x remains the same. And then the second qubit maps to y x or f of bold x. All right. So ufx, dependent on x, is controlled by a register of n qubits in state of bold x, that is an n-qubit register. Okay. Y is the controlled qubit and x is the target qubit here. So again, given such function, given such a unitary transformation ufx, as earlier, the minus phase superposition state 0 minus 1 over square root 2 is an eigenvector. Of the function uf with eigenvalue minus 1 to the power f of bold x. Okay, we saw that earlier in the earlier problem in the second attempt, right here. Okay, so let's keep that in mind. Okay, so I'm going to give you the solution straight away, okay, without bothering with wrong solutions. Now let me draw the circuit diagram for the Deutsch Jozsa problem. It's actually given on page 65. in the lecture notes, okay? But let me draw it here and then explain step by step. So UF is given as a black box. UF has two inputs. The first input is an n-qubit register. So we start with all zeros. Let me make this bold. Okay. This is all. This is n qubits, all in zeros. Okay. And I'm going to apply a Hadamard transform, an n-qubit Hadamard transform. So h to the power tensor n. Okay. This is an n-qubit Hadamard transform. This will go directly to as the first qubit, the first input to UF. And my control bit, I'm going to start with cat1, apply a Hadamard transform. This will be our second input of UF. And then in the output, I'm going to apply another n-qubit Hadamard transform. Okay. I'm not going to do anything with the second output. And I'm just going to measure this n-qubit register. Okay, so this is all n qubits. N-qubit wire. Whereas the second input is just a 1 qubits input. All right. So H tensor n is basically Hadamard transform tensor Hadamard n many times. Okay. This is how we define an n-dimensional Hadamard transform. In the notes, I also mentioned that this boldface 0 can also be denoted by 0 tensor n. Okay. All right. So let's analyze the steps. Suppose that this is psi 0. This is psi 1. This is psi 2. And this is psi 3. Okay. So let's write each step then. All right. So the first step is to initialize the first input register to all zeros. Okay. And then the second qubit is in state 1. So that means psi 0 will be in state 0 tensor n tensor cat 1. Okay, it's an n plus 1 qubit input. Okay. All right. Now what happens if I apply Hadamard transform, an n-qubit Hadamard transform on an n-qubit register with all zeros? Okay. Now we already know the behavior of the Hadamard transform is single qubit Hadamard transform on cat 0. It produces a superposition with the plus phase. But what about applying an n-qubit Hadamard transform on an n-qubit register with all zeros? Okay. Well, as you might expect, it's actually going to produce set of all strings of n-bit lengths with equal 1 over square root 2 to the power n amplitudes. So it's going to produce all 0, 1 strings Now, if you distribute these, you get all strings of zeros and ones, right? And this is n times, right? So expanding this tensor product, if we write it more explicitly, or if we formulate this, so basically Hadamard tensor n applied on an n-qubit register with all zeros will be basically equal to 1 over square root 2 to the power n summation boldface x, and this is an element, this is a string of n-bit length, okay, cat boldface x, okay. So it's the summation of all n-bit strings with equal amplitudes. Okay. So the state immediately after the first Hadamard transformation, psi 1. Okay. Now we're at this stage. Now we know the state of the first qubit, which is actually this superposition. But then we have also a Hadamard 1 here. So the target qubit is in a superposition as well. Okay, so psi 1 will be equal to 1 over square root 2 to the n summation x. So we get cat x, and then we have 0 minus 1 square root 2. Okay. Now, what happens if we apply UF here? Okay. Now let's try to write psi 2. Remember that the target qubit is in a superposition, a minus phase superposition, so it's going to act as an eigenvector. Okay. So because this superposition state is an eigenvector for UF with the eigenvalue minus 1 to the power f of x. So we're going to have a phase kickback, okay, in front of the amplitude of the first qubit, the first register. So psi 2 can be written as, I'm going to apply UF on this whole state, and it's going to be 1 over square root 2 to the n summation minus 1 to the power f of bold x. Okay. The first register will be the same x. The second register will be the same as well because it's going to act as an eigenvector. Right? So psi 2 is supposed to be this state. Okay. Now what happens if we apply the Hadamard transform on this bit? Okay. Because we're applying Hadamard transform on the first qubit, and the first qubit is in a superposition of all n-bit strings with amplitude minus 1 to the power f of x. Okay, so let's look at how Hadamard transform behaves on a single qubit input. Okay. So I'm going to use this fancy x. It's a single qubit. Okay. Now we know that Hadamard 0 is basically 0 plus 1 divided by ket 2, and Hadamard 1 is 0 minus 1 divided by square root 2. But generally speaking, if x is arbitrary, then we can formulate this as, so hx will be equal to 1 over square root 2 0 plus minus 1 to the power x ket 1. Okay, so if x is 0, then this will be 0, right? Minus 1 to the power 0, it's 1. So we get the desired outcome. It will be 0 plus 1. But if x was 1, then we have minus 1 to the power 1. So we have a minus phase in front of ket 1, and we still, again, get the desired behavior. So it can be formulated in this form. But more generally, this is equal to actually 1 over square root 2. We can write this in the summation form. Z minus 1 to the power x times z ket z. Right? What about the behavior of the Hadamard transform on an n-qubit register? So let's keep this equation in mind, and let's try to write the behavior of an n-qubit Hadamard transform on an n-qubit register. Okay. Okay, suppose that we have an n-qubit register, an n-qubit state x. So this can be written as maybe x1 tensor x2 xn. Okay. Now h of x is then h of x1 tensor h of x2 tensor h of xn. And if we write this explicitly, this will be equal to 1 over square root 2, 0 plus minus 1 to the power x1, 1, tensor 1 over square root 2, 0 plus minus 1 to the power x2, 1, tensor minus 1 over 2 times ket 0 plus minus 1 to the power xn 1. Okay, now using some algebra, I can rearrange this equation using the summation formula. I can write this as 1 over square root 2 over to the power n summation z1, z2, zn. So this is an n-bit string. It's an element of 0, 1 to the n. So this will be equal to minus 1 to the power x1, z1 plus x2, z2 plus xn, zn. And then the state is, so I'm basically applying this formula, okay, right here. So this will be z1 tensor z2 up to zn. Writing all together, h tensor n, an n-qubit Hadamard transform applied on an n-qubit register on arbitrary state x is that can be written as 1 over square root 2 to the power n summation boldface z, okay, so z is an n-bit string, minus 1 to the power boldface x times boldface z ket boldface z. Okay, So this is n-qubit state. And basically x times z is the bitwise inner product of x and z modulo 2, okay? So this is bitwise inner product mod 2. Okay, so let's keep this equation in mind because we're going to use this often in the later algorithms. Okay, I'm going to put star here. Okay. So essentially, an n-qubit Hadamard transform on an arbitrary n-qubit register acts in that way. Okay. Okay, so then psi 3, that is the state after the final n-qubit Hadamard transformation, will be, so psi 3 will be, yes, we're here, okay. We're going to write psi 3 after the Hadamard, the n-qubit Hadamard transformation is applied on the first register, okay. All right, so psi 3 then will be 1 over square root 2 to the power n boldface x and minus 1 to the power f of boldface x. Okay, and then we have this factor. I'm going to write this 1 over square root 2 n to the power n summation boldface z, which is an element of 0, 1 to the n, minus 1 x times z. So this whole thing is our first register. Okay, and the second register, we have the minus phase superposition, 0 minus 1 divided by square root 2. Okay, so we add the common factors. Just rearranging the algebra, we have so I'll multiply the amplitudes. It will be 1 over 2 to the n, summation, boldface z, 0, 1 to the n. And then we have the other summation, x, 0, 1 to the n. The common factor is minus 1 to the power f of boldface x plus, so I'm adding the exponents, x times boldface z. Okay, z is our first register. Okay, and then in the second register I have the same superposition. Okay, so psi 3 will be our final state here. Okay, now we're planning to measure the first register and see what happens. Okay, this will be our first register. And this is actually, this part is our amplitude. Although it looks a bit complicated, we will see in a moment that it's actually not, because we're going to take a look at one instance. So Z here actually quantifies over the set of all 0, 1 strings of n-bit length. Okay, but let's consider, so this is actually a superposition of all n-bit strings. But let's consider the component when z is all zeros. Okay, so let's consider the amplitude of all zero state. Okay. Now, for all when z is all zeros, this will be 0, right? So the amplitude of all zero state will be, it is in fact 1 over 2 to the n, right? Summation boldface x. It's minus 1 to the power f of boldface x. Okay. Okay, so this is the amplitude of the 0, 0, 0 state, all zero state. Okay. In this superposition up here, we also have other combinations, okay, with possibly different amplitudes. But let's consider the amplitude of all zeros. Now, depending on the characteristic of the function, whether f is constant or balanced, the amplitude of all zeros actually show a unique characterization. It gets a unique value. So I'm going to discuss the cases. Case 1 is if f is constant. Okay. Now let's consider what happens if f is constant. If f is a constant function, either for all f of x is 0, okay, or for all f of x is 1. Okay, and depending on that, the amplitude of all zero states will be either will be either 1, that is plus 1, or minus 1, okay, depending on the value of fx. Okay, so if we measure the first register, and if f is constant, well, the amplitude of 0, 0, 0 state will be 1. So it's going to return me with 100 probability. The outcome of the first register, the outcome of the measurement will be all zeros. If f is constant, the outcome of measuring the first register is, with probability 1, is all zero states. So I'm going to observe all zeros in the first register when I measure it, if f is a constant function, right? So what about if f is, case 2, if f is balanced? Now, if f is balanced, half of the f of x will be mapped to 0 and the other half will be mapped to 1. But then, if we look at the exponent, when f of x maps to 0, the amplitude will be equal to 1, plus 1, okay? But if f of x maps to 1, then the amplitude factor will be minus 1. So for the first half, for one half, the total amplitude will be 1, and for the other half, it will be minus 1. And then the summation of all together will be just 0. Right? So the positive amplitudes and the negative amplitudes, actually, they interfere with each other, so they cancel each other. Half of the amplitudes would be positive and the other half will be negative, and they cancel each other, so the total amplitude of this state, all zero state, will be just 0. So upon the measurement of the first register, if f is a balanced function, it's impossible to obtain the all 0 state. I will not see as the outcome of the measurement of the first register the state with all zeros. If f is a constant function, I'm certain that the first register, the measurement of the first register will return all zeros. Otherwise, if f is balanced, with probability 1, it's certain not to return all zeros. Okay, so the positive amplitudes and the negative amplitudes cancel each other. And the total amplitude of the state all zeros is basically 0. So for certain, the outcome will not be all zeros. So that means if I measure anything else but all zeros in the first register, then I know for certain that the function is balanced. But if I observe all zeros, then I know for certain that the function is constant. Okay, so this is how we have this dichotomy and how we can determine if a function is balanced or constant by using just a single query. And you can see the power of the quantum algorithm over the classical one. Whereas in the classical algorithm, we need exponentially many queries. It's in the order of big O 2 to the n. But in the quantum algorithm, we have an exponential speed up. So we just use a single query. All right. So I'll see you in the next lecture.